Hello everyone, I, I'm Kamal, and essentially we will be having a short conversation today about modeling multi-day storage assets within the UK energy market, and this was implemented in PLEXOS. The focus really is around a development called MESH, which is based on a compressed air energy storage system. So I will be using the acronym MESH as well as CAES as I talk through the presentation. And this is just mean the Maritime Energy Storage Hub, which is MESH, and CAES, the compressed air energy storage system. Right. So over the course of the conversation today, I will talk a bit about why long-duration energy storage matters. Again, for some, there may not be a need to convince. For others, maybe we might need to have a bit of an exchange afterwards. Very happy to do so. I'll introduce what MESH is from a technical perspective. Again, technical probably in inverted commas. I'll talk about a bit about the optimization challenge, so really what problems or questions that we try to solve. And over that, I'll talk about how we characterize models. And again, see, the last bit of the presentation would focus on some insights. I'd kind of repeat a few themes as I go through that. And finally, bring it back to the theme of the conversation today around human and machine interactions. And finally, some takeaways, and hopefully we can have a bit of an exchange for the next, maybe the last 5 to 10 minutes. So, energy storage. Within the UK, and this is essentially where we're focusing on, we do have over 50% of our energy provided by renewables. And this, of course, comes with its own intermittency and variability, like we understand very, very well, again, given all of us are experts really around PLEXOS. But there's also the phase out of gas assets. So the chart you do see there purports the projection of installed capacity. We expect that by 2050, based on the future energy scenarios, which is an artifact produced by NESO, that by 2050 we will have 6 times the capacity of renewables that we do have today. Now, what is the gap? Now, what we observe from the chart on the left and how that translates to the chart on the right is that we don't have sufficient capacity in terms of storage to really capture all of this surplus power that we expect from renewables. And based off that, we then have an increase in the amount of curtailment on the right-hand side, spanning, let's say, up to 15 terawatts by to the mid-2030s, and again, still substantial up until 2050. These are estimates, and they're very much aligned with what NESO suggests it to be. However, their projections suggest it could be quite high. I believe a Montel analysis analytics report suggests that by 2025, we had around 10 terawatts of curtailed power, renewable power essentially. So the idea of long-duration energy storage is really to be able to capture all of or most of this power and essentially provide a multi-day dispatchable asset that can essentially enable the flexibility, but also support a grid that is essentially constrained, but beyond that addressing the potential of scarcity of renewable power within the system. Now, what is MESH? I mentioned earlier it's the Maritime Energy Storage Hub. It is essentially a cluster for storage. So the schematic on the right-hand side there does show what MESH is. So the core of it is a compressed energy storage system. So on the left-hand side, you can see the compressor trains. So essentially the half triangles that are driven by a motor, which is electrically powered. And on the right-hand side, you have the expanders, which essentially produce the power. So it's almost, you could say, like a sort of gas turbine in the middle. Part of the operational mechanism of mesh is that it's supported by offshore wind farms within the area. It is located about 40 kilometers, say west of the shore with regards to the east, with regards to the East Irish Sea, but also again fundamentally it is a 2090 megawatt asset, 55 gigawatt storage. 190, again, that's not a typo, it's a really long duration asset, and also provides multi flexibility. The idea with regards to operation of this asset is that it can provide support for the wholesale market, balancing mechanism, capacity market as well, again, given its long duration, and of course, ancillary services, just because it's also dispatchable. Now, in terms of context of potential comparison, it is supported by a salt cavern, which is again a subsea asset, which would again formed by etching salt formation within the East Irish Sea. A 650,000 meter cube of storage. That's like 290 Olympic-sized swimming pools, so it's really, really large. What does that convert to when you talk about storage itself? So you compare it against battery storage, again, 1 to 4 hours, could last, again, up to 8 hours, again, given the new batteries we're seeing today. Pumped hydro, that can go up to, say, 2 days, for example, but mesh takes it a step further. So that's really about 7 days or slightly more than 7 days of storage that the asset can provide. So what really is the question? Given we understand now what mesh is, what were we really trying to solve? There are 3 key questions or 3 core questions that the client required an understanding. The first is energy availability. So if you do have a storage asset, one thing that you benefit from is understanding that if you locate it within a certain environment, you would like that you have sufficient power to support the asset. So the client wanted to understand how much curtailed power do we have available within the location of where mesh is. So this requires, let's say, a multi-pronged approach to understanding spatial awareness, so location, but also temporal. So how does that curtailment vary across over time? The second question is system value optimization. So when you know how much power you have that you can use to support mesh, the next question is, have you optimally sized the asset? Again, this working with our core engineering teams at Siemens Energy, we're able to implement some, say, optimizations around this. But beyond that is how might the asset create value? So how do you make money off the asset? And finally, ensuring that you have a robust investment consideration of the asset. So evaluating potential sensitivities, let's say around prices, CapEx, OpEx, and of course, ensuring that your revenue stack is reliable. Taking it a step further, when we focus squarely on that system value optimization, the methodology would look something like this. So you build your price evaluation. Of course, this we've talked about quite a lot today. So you do have a characterization of the energy system, and you try to predict prices based on fundamentals. Next is the topology characterization. So you want to understand you have an asset that has probably never been modeled before within any software, but you want to be able to capture as much of the engineering into the commercial model. That then leads to, of course, capacity expansion, optimal design, and sizing the asset in a way that would, of course, create the most value. And then we move on to the economic dispatch. So how does the asset interact with the market? Very likely you may need to do this multiple times. Again, we saw presentations earlier that talked about a single dispatch to start with, and then you priming the next dispatch just based off committed positions based on the prior dispatch of the asset. So why essentially is mesh different? And the fact that it is a multi-day storage, so you're not necessarily trying to cycle daily. It also has a large inventory, so essentially your storage is it's for very long duration. You will have to be very strategic as to how you utilize the inventory of the asset, but also the integration of physical constraints. Like I showed earlier, it's not a very simple asset. You do have compressors, integral compressors, you have limitations from an engineering perspective, but looking at it as well from the generation perspective, you have expanders that also need to be considered based on the engineering limits. And that engineering leads very much so into what this is. So how do we translate the engineering bit into PLEXOS? So part of our considerations bordered around the cavern, its pressures. So we had an operating pressure of around 118 bar to a minimum of 50 bar. How do you translate that into what PLEXOS can understand with regards to storage size? Compressor systems, so you have power limits, minimum stable load. You might need, of course, the MIP optimization, obviously, to respect such considerations. Expanders, grid connection, which is also one of our considerations, and finally, market participation. So in order to enable this, we worked with our core engineering team that focuses on CAES design. We also worked with market experts within our teams as well, in order to be able to translate all of these considerations into what PLEXOS can understand. So for the cavern itself and the connected storage asset, we use the pump hydro storage system within PLEXOS, but essentially representing the storage in a way that it mimics essentially the salt caverns for the mesh system. We also represented, of course, power and efficiency curves within PLEXOS, and finally representing markets in a simultaneous fashion. So what this then did was it defined what the operational behavior of the asset is, which essentially is a multi-day dispatch, strategic inventory, market interaction, so being able to characterize multiple markets. So within PLEXOS, you can introduce a single market that's forward-looking, and of course, another market that is more real-time, and then the system helps you re-optimize that or redispatch your asset based on, of course, committed positions. And finally, the constraint-driven operation. The engineering, especially for this kind of asset, cannot be overlooked because it helps inform really how much realism you're infusing into your modeling approach. So the tagline essentially for this particular point of the conversation is that the critical optimization, chronological optimization that we use for the asset required physical behavior of mesh to be represented as explicitly as possible through essentially time-dependent operational constraint. Now, what might the operation look like? Now, this is just an excerpt of what the operation looked like, and you can see it's fairly different from what you'd expect a battery to do, or maybe a 2-hour or 4-hour battery to do. Here on the left-hand side, you do see mesh charging over, say, what is almost about over 24 hours, and it holding its capacity over a few hours, charging additionally, and then discharging over a significant period. So the black series here suggests the price on the system within that particular time, and the series below suggests meshes storage. Now, what does this say? It does say that the dispatch is quite sequential, so we're not necessarily cycling over a single day. The inventory was also preserved, so when we got to, say, somewhere around 6 o'clock on the 30th of March, PLEXOS realized that it can make more value by holding its inventory and then keeping that for when it can dispatch later on, because it has, again, perfect foresight of prices in subsequent hours and subsequent periods. There's also that future flexibility. So the fact that you do have inventory now doesn't necessarily mean you must dispatch now. It means that you can hold and potentially gain some economic value by keeping the power. Finally, as well, the constraint shift the operation. So a lot of this is informed by the constraints within the model, which are largely driven by the engineering consideration for mesh. Now, I'll highlight this, essentially expanding on this on the next slide, so I might skip it just for the sake of time. But in terms of how we consider modeling for say, long-duration storage asset, the modeling approach that we use essentially informs what kind of value that asset can provide. And this would hopefully, when we talk through it, highlight why the methodology essentially matters for how we inform a long-duration energy asset. So on the left-hand side, I've considered some of what we'll typically perceive as, how we model batteries. And sometimes we might perceive LDS, so essentially long-duration energy storage assets, as things that we could essentially model by just replicating what we do for batteries and extending the duration. However, for an asset like this, you would need to consider much more than a simplified approach. So the multi-day-ability is one thing that you probably wouldn't necessarily consider for a short duration asset. The extended optimization horizon, so not necessarily 1 day or 2, in this case over a week. The explicit engineering constraints, and this is really key just because if you don't capture this as realistically as possible, very likely you erode value, and we'll see that very soon. And finally, the future operational optionality. What we understood is how we do model long-duration energy asset determines the kind of value we observe for the asset. Our analysis also shows that if you do simplify your approach, you have a potential of eroding 60% of your assets' value through the process. But why does the modeling really matters? You really want to capture the operation of the asset as best as you can. You want to ensure that you're capturing the value of time also correctly. Finally, you're respecting physical constraints, so you don't want an operation that isn't necessarily feasible. And finally, preserving future choice just because it's a long duration asset. Now, taking it a bit further into that human machine interaction, which we again discussed around, the keynote as well as the conversation with Prajwal and Wafa, is what essentially is the impact of that human expertise in such a modeling methodology. So our expertise is really focused on the engineering interpretation. So how do we listen to our design team within Siemens Energy that have very great understanding of technology? How do we convert that into what PLEXOS can understand? And how do we implement a commercial model based off that? How also can we integrate with our market analysts and modelists to be able to ensure that we're capturing drivers of the system, but also drivers of revenue as best as we can within the model? How do we represent the asset behavior? So things like efficiency, degradation, reservoir dynamics, as well as losses. How do we ensure that we're also capturing that? Scenario definition. So we talked about this earlier. What scenarios are ideal? Which ones are realistic? Which ones are sensible? Which ones help us really capture the potential uncertainties and, of course, validating results? So it's great to have solutions, but you want to be sure that they're giving you what you need. And on, of course, the machine side, we saw demos today around what AI can do, around, again, the dispatch of assets, multi-market optimization, constraint enforcement, revenue estimation. I think there were some really great demos around that. And finally, the sensitivity evaluation. So this two essentially inform a potential framework around first, understanding the engineering, formulating the model, even from a problem perspective, prior to you defining or characterizing anything within PLEXOS. The optimization output would then be informed by the machine itself, the expert interpretations. How do you interact with that output? What decisions would you like to make? What insights is it telling you to do? And of course, you need to refine your assumptions. You need to modify things in order to ensure that you're capturing things as realistically as possible. So essentially, in order to create credible insight, it has to be an iterative interaction between human and model. And of course, finally, this matters because optimization quality depends on engineering realism. You do have human interpretation, which remains critical I understand AI is taking over, but it is still critical to commercial insight. And finally, the iterative refinement produces models that are credible. So you will have an interaction between what you think of things as well as what, again, the model is providing for you as an output. So again, I'm boiling this down back to some very key insights so we have a bit of time to exchange, and I'm happy to go back to certain slides in order for us to discuss. So what essentially does this inform us about modeling long-duration energy storage assets? Chronology does matter. The methodology that we use shapes the value that we observe within our assessment, especially for investment analysis. We want to be sure that how we're defining our problem and, of course, implementing it ensures that the output that we create, the commercial insights that we create are as realistic as possible, and only then can we make the best investment decisions. Engineering realism also matters. You want to set constraints that align with what, again, your technical team are suggesting. And finally, the human interpretation is vital. So I know there was a question earlier today really around where does that split occur between what AI can do and, of course, what a machine should do. I think interpretation is key. So how do you go from insight to decision making? That I don't think should be driven by AI. Of course, can be supported, but the decision itself has to be human. All of these boils down to the fact that long-duration storage assets behave fundamentally different when you consider chronology, engineering realism, represented, of course, explicitly within your modeling framework. And of course, accurate valuation of long-duration energy storage asset essentially requires the right balance for your chronological optimization, engineering realism, and finally, human expertise. With that, I think I'll pause here for questions. I've kind of given a monologue, but if there's one thing that you probably take away today is that how we model long-duration storage asset really and increasingly determines the value we observe for such an asset. Thank you. I think we do have a few minutes for questions, and be happy to take as much as we can within the time available. Was it? All right, great.
Hey, first of all, thank you for this very interesting talk. The 190 hours you said, is that also coming from optimization, or is this coming from physical restraints?
Right, that is essentially an optimization, however, within some very, very hard to define constraints. So the geophysicists within the team did suggest a limitation for how much storage we can have within that location. This is largely informed by salt formation. However, we also performed additional modeling just to see if there was a case for a larger storage, which really didn't provide much value. So I'd say it's a combination of both the physical constraints on the geophysics level, but also the constraint from an optimization level.
Did you compare the investment costs comparing to the battery storage, which could be very, because it's very sophisticated solution. Number of compressors, number of burners, everything. So it's not a common out-of-the-shelf solution.
It is true. It is true that it's not a common asset. Well, the cost of this, again, I would have to be very cautious here, but it will run into, it's over £500 million in terms of investment. Now, if we think about it, if we had to define a battery storage, lithium-ion battery that can provide 190 hours of storage at 290 megawatts, I would almost wager that you will get something higher than around £500 million. But in addition to this, one of the insights the client was going for was to do something very different. And the novel approach provides additional benefit in the sense that this is dispatchable. You don't really get degradation per se. You don't really have, that cycling issues. You don't have the repowering cost, of course, that will come with the battery. So all of these considerations, I think, inform the client's technological choice. Now, this is not to say that there's no case for a really large battery. Again, there are 10-hour, 8-hour batteries in, say, Australia, for example. Within the cap and floor scheme for long-duration energy storage in the UK, we do have batteries on that. They're, again, over 8 hours. But I do think that the client's focus here is to provide first dispatchable power, but also to create something that is very novel and creates much more value to the system. Great. Any other questions?
What was your setup in PLEXOS in terms of the sort of look ahead, the MT, the ST, and what in coming up with the model that you ultimately used, what did you play around with and find did and didn't work? And I suppose, as well as that, how complex was the rest of the model? Did you have to simplify other things in order to get a good representation of your asset, and would it work if you also had to be modelling many of these assets in a much more complex system?
Right. Really good question. Very compound question as well, but really good. I think if we go back just slightly to the methodology framework, I think each of these core questions have their own workflow. And I think on the left-hand side, that's more system model, because the insight there is, or the intention there is to create, again, what curtailment looks like. So you're limiting assets dispatch based off thermal constraints, so network limitations, but beyond that, it is the economic constraints. So they're not dispatching just because, again, the price doesn't really make sense for them to do so. The core one, which is the revenue model, that, again, is informed by prices, like we saw here. So the price was exogenous rather than endogenous. So that simplified the model significantly, because the focus now is on the asset itself. So the focus was the asset and the market. So how do we play around the market to ensure that we're capturing forward markets, but also, of course, the real-time market. What didn't work to start with? I think the market was a bit of a concern to start with, just because there are lots of constraints within the model, and this is just to be able to capture as much as possible the engineering realism within the system. So we had to work in how the markets essentially interact within PLEXOS, and ensuring that forward markets really behave like forward markets, and you don't have say a potential where your day ahead and intraday are essentially competing, because that's not really meant to happen. I think that was one challenge we had with the analysis, and I think one other thing was also when you characterize a real-time market within PLEXOS, one thing that isn't very clear is how PLEXOS does the re-optimization for you. As such, you might need to, whilst you run a single model, you might need to split your run in order to understand really what PLEXOS is doing differently, in order to be able to explain that behavior. So that's one thing that we had to do to make it work. But yeah, I hope I did answer your question, but happy to have a longer conversation over the next few hours. All right then, thank you so much.